Hi, doctor. My name is Zhao Chenbo, and my metric number is 227220. So now I'm going to demonstrate Lab 7. So first we go through the ENSP configuration. So for this lab, mm, it's about a single area OSPF network implementation based on the Area 0. And the primary objective of this employment is to establish dynamic routing, ensure the network resiliency through the DR or BDR placement. And our topology consists of these core routers, R1, R2, and R3, uh, interconnected via broadcast multi-access segments alongside loopback interfaces, mimicking internal local Z networks. And for the step one, for router one, uh, I initialized the system by rename the device R1 to keep the environment organized. Then assign a distinct subnet IP to interfaces gigabit Ethernet 001 and the subnet IP is 10.0.12.1 to face router 2 and and another IP gigabit 000 to face R3 and the IP is 10.0.13.1. Um, and finally, I create a logic loopback zero interface initialized with 10.0.1.1 to stimulate an internal network segment. And for router 2, similar to R1, we configure the host name as R2 and provide the physical link gigabit 001 with IP 10.0.12.2 to match router 1 subnet and instanted lookback 0 at 10.0.2.2. And this for R1, router 1, router 2. And then for router 3, we established identified as R3 and I configured its physical interface gigabit Ethernet 000 to targeting router 1 using IP 10.0.13.3. And for local networks, we construct two separate logic environment. Loopback 0 mapped to 10.0.3.3 and additional loopback 2 mapped to 172.16.0.1, which later acts as an external corporate boundary. And then for step 2, it's about core OSPF activation and L0 boundary mapping. First, for router 1, we spin up OSPF access 1 and explicitly tie it to a unique router ID of 10.0.1.1 for clear identification inside the link state database. And then we enter the configuration boundary for area 0. It is a backbone area. Rather than enable OSPF globally, we utilize the inverse wildcard mask 0.0.0.255 to precisely instruct the router to run OSPF exclusively on interfaces falling within the 10.0.1.0, 10.0.12.0, and 10.0.13.0. And then for second for router 2, We mirror the configuration by enable SPF precise ones to to ensure to ensure they can share the exact same link state database. And then we assign the router ID to 10.0.2.2 and bind the networks 10.0.2.0 and 10.0.12.0 to area 0. And this is for router 2. And for router 3, we complete the baseline OSPF grid by running process 1 with router ID 10.0.3.3, and we introduce its local segment and its transit network into area 0. And again, we we can see the result showing a successful full loading state with R1. And then for step 3, global routing control plan verification. First for router 2, we call up the global IP routing table to verify data propagation and dynamically populated routers with protocol flag OSPF, specifically learning the passes to router 1's loopback and router 3's loopback. And for router 1, we pull up a brief summary of the OSPF. Here's this cleanly demonstrate that router 1 is fully established neighbor state over both of its active physical interfaces simultaneously. And for step 4, it's about OSPF timer manipulation, mismatch isolation. And also for router 1, we can display the current OSPF operation trains of interface to prove that protocol defaults to a 10-second hello interval and a 40-second dead interval on broadcast networks. And we explicitly modify these items on interfaces G000, raising the hello tracking to 15 seconds and the safety dead timer to 60 seconds. And then for the router 3, we resolve the network outage by adjusting router 3's interface G00 to match router 1's updated timer. And all this is all for the router 3. Next is step 5. For the step 5, we created a standard. We created a standard static default router 0.0.0.0, blah blah blah, pointing outwards through your router. Through their router 3 designed isolated boundary networks, and to avoid the tedious chore of manually configuration static routers on every devices in the building, we enter the OSPF precise one and instruct the protocol engine to auto advertise this default router down the line. And then for the router 1 and router 3, no, router 1 and router 2, we run a final pin check, 172.16.0.1, and this proves that traffic from an inside router can travel successfully across intermediate hops using the dynamically injected default router. And then for the last step, step 6, for the router 1, We check the peer profile for router 3 and the router 3 elected itself as the designated router and relegated router 1 to the backup designated router. And the theory because both interfaces started with a standard default priority of 1, and the election was decided by the highest router ID, which allowed the router 3 is 10.0.3.3 to beat a router 1. And to beat router 1, 10.0.1.1. Um, and then also for router 1, I manually override this behavior to elevating router 1's interface priority value to 200. And then we we set its local interface's priority value to 100 for the router 3. Uh, and then for the router 3 to focus the router's flipping. No, to focus. We we need to focus the routers to accept the new configuration, and then I manually execute a shutdown followed by an auto shutdown. This command sequence on both shared interfaces to trigger a clean reelection. And then for router 1, I verified the final outcome by executing display OSPF peer 10.0.3.3. Show It shows that R1 now is officially verified as a primary designed router for the segment, completely fulfilling our engineer design goals. And for the last, I displayed the current configuration for router 3 for the 3 router. Okay, so that's all for lab 7. Thank you for listening.